All right, up next. Finding the speed of a circular orbit. All right, so let's think about what happens if we've got something orbiting a body, like the Earth or the Sun or some other massive structure. So we'll have a satellite or something similar. We'll say it's traveling with some speed v, and it's going around following a circular path. So there will be some distinct distance between the center of the object that is being orbited and the center of our thing that is doing the orbiting. All right. The first thing we need to think about is what forces will be acting on that object as it orbits. And as luck would have it, there really is only one. So let's see. This should have been labeled as radius r earlier. Actually, I'm going to put it in blue. And let's see. The only force that actually acts is the gravitational force pointing towards the center. And can we use just that to figure out what's going on? Yeah, we can. So remember that sum of forces is equal to ma. This is Newton's second law coming right out of chapter 5, your 1A class. So as soon as we introduce Newton's laws, we've got this. We only have one force. We know exactly how that force works. So it'd have g times mass of the central body times mass of the orbiting body divided by the distance between their centers squared. And that would be equal to m times their centripetal acceleration. I'll even put the r hat in here for the direction. All right, well, what type of acceleration is it? Well, it's following a circle, so that means a would be our centripetal acceleration. And looking at this, that centripetal acceleration would be pointed towards the middle here. Centripetal acceleration has a size of v squared over the radius of the circle. And in this case, I would point out it is also in the minus r hat direction. All right, so here's what we end up with. Minus big G mass of the central body times m r hat over r squared is equal to mass of the orbiting body with a minus in front because I'm going to put the v squared over r with the r hat out here. We're kind of lucky. The mass of the orbiting body cancels out. The r partly cancels out. The minus sign cancels out, and we don't care about direction anymore. So we're finding that g times m, the mass of the orbited body, the central body, is equal to v squared. Now this is actually a great stopping point if you're trying to figure out the kinetic energy of a circular orbit. But we wanted to figure out what is the energy of an orbit, so we'll actually take that square root. G times mass of the central body divided by the distance the object is orbiting at center to center. If you're thinking about this instead as the body is orbiting, say, here with some altitude h, and then the planet has some radius r, you can rewrite this in another form to deal with the altitude. So you'd say g times mass of central body times radius of central body plus the altitude above its surface. So that's for when you're worried about altitude. Okay. Now again, this is useful in all three of these forms under different circumstances. If you're trying to find kinetic energy, we'll actually stop at the gm over r equals v squared step. If we want the v for an orbit, it depends on whether we know the center to center distance or whether we know the radius of the object and the altitude, which of these two you would use, but they're more or less equivalent. Now I should say I normally expect you to derive these on the fly because understanding this idea that it's really just a direct usage of forces from your 1A class. The thing that you're kind of trying to acquire here is how do you think about problems, not just memorize a bunch of formulas and try and apply the memorized formulas. There are too many formulas to memorize, and most of them are not worth the time. So the emphasis in your mind and in my teaching should be on process. And in this case, the process is if I have a circular orbit, I should be able to just think about that with F equals ma because I know the size of the force thanks to gravitation. And I know the size of the acceleration in terms of the same kind of things, thanks to it being a circular orbit. So try and focus on process. All right, that's actually going to be it for this video. We're going to talk about total mechanical energy of a circular orbit next. Then we'll talk about period. And at the end of all of that, we're going to do a problem that kind of sums it up.